All right. Today we're going to talk about exponential numbers, exponential functions, extremely important concept to know in the nuclear industry. This is how reactor power changes exponentially, which exponentially just means, fractional change. So reactor power does that. We have radioactive materials that are radioactive decaying exponentially. We put up radiation shielding that is reducing our radiation shields exponentially. So it's extremely important that you understand how to solve for exponential functions and solve for all different variables in the exponential function. So we normally start out with some sort of number, some sort of final number. So we'll just say, here's a final number equals some initial number and some sort of exponent. A lot of times we use the natural exponent e, which is, you've already studied, equal to 2.71 something or other. And then we have some sort of variable up here. We'll just use x for right now. The first example I'm going to use of this type of problem is the changes in reactor power. We shut down our reactors periodically to do maintenance to them. And when we get ready, we have to start the reactors up. And when we start up the reactors or we shut down the reactors, they change exponentially. It takes a certain amount of time to go from 100% power to 50% power when we're shutting down. And then if we keep going at the same rate, it'll take the same amount of time to go from 50% power to 25% power. See, it's always cutting in half, or you can cut it in tenths, or however you want to do it. It's exponentially, fractionally changing. So the equation well, there's several different equations we can use, but today I'll go ahead and say, all right, what if we're a reactor that likes to use the term reactor period for changes in reactor power? Well, we have power final equals power initial e to the time. I'm going to make that t a little bit better here. The time of our power change over tau, which is our reactor period. So going through these, PF is our final power, final reactor power, after the power change. P0 is the initial power initial, before the power change. And T is the time of the power change. So maybe it takes us an hour, maybe it takes us 15 minutes, whatever. We're going up at a constant exponential rate during this certain amount of time. And then tau is equal to what's called the reactor period. And the reactor period is defined as the time required for reactor power to change by a factor of e. And remember that e is an irrational number, but it's equal to it's approximately 2.71. Okay. So if we talk about reactor period, just before we get into all the math with exponents, let's just talk about reactor period so that you get a good solid understanding what this is. Let's say that we have a reactor period of 1 minute. So we're going to say tau is equal to 1 minute. And let's say our initial reactor power is equal to 10 watts. What would the final reactor power be 1 minute later? Well, if the definition of reactor period is the time required for the reactor change by a factor of 2.71, and we let the reactor change at this tau of 1 minute for 1 minute, then it's going to go up by a factor of 2.71. So 2.71 times 10 watts, it would end up, the final reactor power would be 27.1 watts. And so that gives you a feel for what this reactor period is, how this time required for the reactor power to change by factor 2.71. All right, so now we're ready for us to do a little more complex problem where we do need to use the math. And so in this first exponential problem, I'm going to say, all right, let's say we have a reactor that starts out at an initial power of 150 watts or kilowatts. Let's do kilowatts. So kW stands for kilowatts. And for you to understand what a kilowatt is, you're understanding the SI prefixes and things, but how much is a kilowatt of power? Well, just to let you know, 1 kilowatt of electricity is about equal to running an electric skillet at home. Okay, so 1 kilowatt of power will run an electric skillet while Mama's frying chicken. All right, so we go on here and say, all right, let's say this same reactor has a increasing reactor power of plus 200 seconds of reactor period. So that means every 200 seconds it's going to be changing by a factor of 2.71. Okay, so this is kind of a fast changing reactor. Normal values of an up power somewhere 100, 120, 150 seconds. 200 is kind of pushing it, but we're gonna move this reactor right along. And then let's just look at, let's talk about our time here, and let's just let this reactor increase in power at this plus 200 seconds of reactor period for 15 minutes. So filling in our equations here, we want to solve for, well, what is our final reactor power going to be if our initial reactor power is 150 kilowatts? Okay, so it's right now being able to support 150 electric skillets. And then it's going to go up by a factor of E to 15 minutes. That's the time of our increase, how long we allow it to increase, divide by plus 200 seconds. Now, one of the issues that we have is that every time you look at a base, doesn't matter if it's E, base 10, 2, whatever this base is here, we have to have its variable have no units, because the exponent is always just a multiplier. The base and exponent together is just a multiplier, and it should just be a fractional change, and it shouldn't have any units to it at all. So up here, where we got the minutes divided by seconds, we need to change that and get rid of those minutes and seconds. And so one way we can do that is say, all right, what if we say that 1 minute is equal to 60 seconds? Well, now our minutes will cross out in our unit conversions. Our seconds will cross out,